So the first thing that you need to do is always, always, always start with a free body diagram, okay? All right, so this says she has a mass of 72 kilograms standing on a scale in an elevator that's accelerating upward. What will the scale read in newtons? Okay, so first of all, our free body diagram has how many forces? How many forces does Sally have acting on her right now? Okay, Thomas says 3. What 3?
Gravity, normal force, and acceleration.
Acceleration is not a force. Okay. What?
Applied force?
No applied force. Okay, when you stand in an elevator, on a scale, when you stand on the scale at all, the scale's job is to tell you basically how much force it's having to exert upward on you to keep you off the ground, essentially, okay? So gravity's pulling down on you. The scale is exerting an equal and opposite force in the upward direction. That's if I'm at rest, okay? If I'm accelerating, it's going to have to exert either more of a force or less of a force. But when we stand on a scale, the scale itself is exerting a force upward, which is essentially to us the normal force, because we're standing on a surface and it's exerting a force in the upward direction. So essentially what the scale reads is the normal force. Okay, so you can label it F sub scale if you want. You can label it F normal, like regular problems. Whatever you choose to do, that's fine. But she only has 2 forces acting on her. Okay, so our free body diagram looks just like this. F sub G and F sub N. You could label that F scale if you want. It's essentially the same thing. Okay, because the scale is exerting a force in the upward direction. That's what a scale tells you. It's how much force it's having to exert. A regular scale you'd have in your bathroom obviously converts that to pounds. Okay, it doesn't read it to you in newtons. But we want our reading to be in newtons here. Okay, so after you have this free body diagram done, your next step is to start your F net equation. Okay, are we looking at vertical forces here or horizontal or both? Only vertical, okay? And when we look at vertical forces, we take up forces minus down. So F sub N minus F sub G. So this is an equation that you need to have every time before you start plugging in any numbers, before you start doing any substitutions. These are 2 things that you should have, is your free body diagram and your F net equation. Okay, those are important for you to have. Okay, now we can start doing some substitutions. So what can we substitute in for F net? M times A, mass times acceleration. So our mass was 72. Our acceleration is what? 2.8. Is it accelerating in the positive direction or the negative direction? In the positive direction. You have to be careful when you're reading these. If it says it's accelerating downward, you have to include that negative in your overall acceleration. Okay? We don't have to include it in our gravity because we account for our negative right there with our minus sign. Here, in our overall net acceleration, we have to include the direction in which it's going. So here we're going positive, so we're going to keep it positive 2.8. We're solving for the normal force or the scale force. And what can we substitute in for F sub G? Mass times gravity. So we're going to take 72 times 9.8. Okay? Okay, so we've got 72 times 2.8, which is 201.6. Which means our normal force or our scale reading is equal to what? 907.2. And that's it right there. Okay? Is this scale reading a larger number or a smaller number than if she was at rest? It's reading a larger number. Okay? Because think about it this way. When I'm standing in an elevator and I'm accelerating in the upward direction, I'm moving upward, which means my gravity's pulling me down with a greater force, okay, so it would seem to this scale, right? The scale's moving upward, I'm trying to stand still, or gravity's trying to pull me back down, so I'm exerting a greater force on that scale, which means the scale has to exert a greater force on me. Okay? If I'm moving downward in my elevator, that means it's kind of taking some pressure off the normal force, so you get a lower reading than you would if it was at rest. That make sense? Okay. What other types? We want to do, what other types of problems did we want to do? Oh, like with two hanging objects? Where is my tension?
Or the one with like the
Like a
tension
string between the
String between the box. Okay, I'll have to make that one up off the top of my head, which could be interesting. We'll see. Okay. When I make up numbers, that means things could go crazy. So, it might not work. I'll try it. All right, I'm going to give you one to try while I am finding a problem like this, okay? I'm going to give you a different type of problem to try while I'm finding one like that, and then you will. Okay, let's try this one, this first one. Okay, while I find that other problem. Okay, so we found acceleration because we have our final velocity, initial velocity, and our time. So acceleration equals 3.21. Here's our free body diagram of our car. Sorry, our free body diagram. So we've got gravity, we've got our normal force, we've got some sort of applied force, and some sort of frictional force. Our overall goal here is to find what applied force, so what force is the car having to actually output to counteract friction in order to get it to accelerate at this rate. Okay, that's what our overall goal here. So we're solving for our applied force. So F net equals F applied minus friction. We're going to substitute what in right here? MA, right? So mass is 1800. That's 3.21. We have 230 newtons of friction. So we're going to basically multiply those two together, then add over our 230. So 1800 times 3.21 plus 230. So 6,008 newtons. Okay, so let's start with our free body diagram. First, every time, free body diagram. So we've got some force applied at an angle here. 2,000 newtons. What other forces do we have acting on our car? FG, good, and the normal force. Okay, it's still resting on a surface, so we have both of those things. We have to first and foremost break down this initial velocity, this initial force that's at an angle. So what would I label this side as? Right here? F applied Y, good, or F pole Y, or whatever you want to call it. And this side would be F applied X. Okay, when we're talking about acceleration here of a towed car, are we talking about vertical acceleration or horizontal acceleration? Horizontal, good. So we only really care about our horizontal net equation. Okay, so F net in the horizontal direction is equal to rightward forces minus leftward forces. So what's our rightward force here? F applied X. Do I have any leftward forces? No, so I can go minus 0 there. Okay? So now I can start plugging in numbers. I can start doing my substitution. So what do I always substitute in for F net? Mass times acceleration equals F applied X. I can solve for F applied X by taking 2,000 sine or cosine? Cosine of 35. Okay, which means I'm going to plug that in there. I'm solving for mass, which means I'll divide by my acceleration. Okay, do we agree on our mass here? I want to take this one step further, and I want you to solve now for the normal force. Okay, solve here for the normal force now. So we've got our mass. Now we're going to be able to solve for the normal force, so I want you to go ahead and do that. Take it one step further and solve for the normal force. Go ahead and try and do it on your own. I'm going to work it on the board if you get stuck, but go ahead and try and do it on your own if you can.